Right, we just started the session on rate equation. Rate equation. Yeah, oh, I actually have to intro with Leo. One copy for each student. And okay. So
right, testing. Okay. So you can know about the meeting detail here, and then we'll pick up from where we were last time. Okay. So last time we stopped at like the derivation of the units of rate constant and equilibrium constant. Okay. And we mentioned that they are different, right? So you see the unit vector. Yeah. So check to see that your worksheet has two sides. Okay, so it should be printed on both sides. Okay, and all four sides should be different. If you find any two sides the same, you can come out and get another copy. So we'll work on these questions together. So we'll work on these questions together. But first, let's continue with our discussion last time on the units of equilibrium constant and rate constant first. So, yeah, So what about the second equation here? So we have two examples. So this was the first example, and this is the second example. How do we write the equilibrium constant of this second equation here? Anyone? When we have A plus B becoming C plus 4D. C. We don't do plus.
Equilibrium.
Yeah, we do equilibrium, and also what's the relation between terms? Do we do multiplication or do we do addition? Multiplication. Okay, so I know what you see here. You see a plus sign. But when we turn this into KC expression, we will write a multiplication sign between terms. And each of them, they should be raised to a power of their. D will be raised to a power of 4, and basically every number will have to be raised to their own power of their whole ratio. And then you will divide by the concentration of A at equilibrium times, I really want you to know that this is multiplication. This is not addition. Okay, as I see some students still make mistake on here. Okay, they thought it is addition, this is not. So concentration of B raised to a power 1. So what is the unit of equilibrium constant here? Remember the trick I taught you? You can, I know it may not be easy dealing with mole per dm cube, right? So why don't we let M, we can use this trick. Let M be, so capital letter M are there. So capital letter M means molar, right? So it means mole per dm cube. You can now rewrite mole per dm cube as M to make your life easier. So you can see now, we have M to the power 1 over M to the power 2. So what is M to the power 1 divided by M to the power 2?
1 over m.
Over M, or M to the power of
Negative 1.
-1. Then now you can expand it, okay? So this will make solving for the unit a lot easier. So can you now do expansion? So when you multiply -1 inside, what will the unit become? Mole, -1, and dm cube. Yes, so we have dm cube mole -1. So use this, I want you to use this trick now to solve for this. Okay, right. So then, Janet, together with the other students, they can refer to the video later. Okay. So so now can you tell me what should the unit be? Let's use the same trick we just used. Okay, let M molar be mole per dm cube. So how many molar times are there in total on top? 5. So we write M to the power of 5. And how many at the bottom? 2. So can you solve? Can you simplify it?
3.
Yeah, molar cube, yes. Okay, and can you now expand the cube back into mole per dm cube? So you have mole per dm cube all to the power of 3. So remember, when you expand it, mole cube dm -9. Is that clear how we get to the unit? I'm bringing this up again because in unit of K we have a similar thing happening. Okay, just that we have to take things up a notch this time. So we have mole cube dm -9. You see, we have a tendency to write the positive exponent term first, which is why If you're wondering why am I swapping the order, why am I suddenly writing DMQ first? That's because they have positive power. We write the positive power term first before the negative power term. So you can put down this note on the side. Yeah, so you can write the note. Positive power terms are written first. Okay, so they are written first. It's just a convention, okay? So now on the right, we do the same thing, okay? So we have two examples here. So we have example 1, we have example 2. So as usual, if this is too hard to simplify, you can write mole per radian as molar first. You have molar s to the power -1 on top and molar at the bottom. Well, it's very easy for you to see that it will simplify to just per second. Okay, so we are swapping mole per radian for molar. So we have this, and now I want you to solve for the second rate constant here. I want to know what the unit is for the second rate constant. So what is the unit of rate again? Molar per second, yes. So we have molar here, so this is molar. So if we use the simple unit, this will be molar per second for rate, and just molar for concentration. So with this in mind, can you put these units back to where they belong? So you have rate. What is the unit of rate in terms of molar? Molar per second. So can you do molar per second? And how many constant units do you have at the bottom? You have 2, so therefore molar squared. So can you simplify this? It's like one of those math questions you see now. Math class like a cubed b over the b squared. You just simplify it. Okay, so can you simplify this? It will be molar. Let's write molar first. -1 as -1, right? And then you can expand back the mole per DMQ. So this is what I recommend that you do. Okay, instead of really trying to solve it using mole per DMQ, simplify it as m and then expand it later. There's a lower chance for you to make mistake if you do it this way. So what is the final unit? DMQ. Mole -1.
Second one.
S -1. So it's kind of scary, right, the unit? But if you know where it comes from, then you see it's actually quite easy, okay, to solve. So just let this be m first before you actually expand the mole per radian. This is my word of advice to you, okay? So you have equilibrium constant and rate constant. So now let's do a very quick recap on the rate equation on the order first, okay? Because you need to know what order means before we can move on with the worksheets we have today. Okay, there's a few worksheets. So just a very quick recap. Rate of reaction and order of reaction. There are only 3 types of orders you will encounter in DSE. They are 0th order, 1st order, and 2nd order. And I want you all to jot it down on your notebook, please. Okay, this graph. So there are 2 graphs that I want you to copy. One for each order. So you have concentration time graph. This is the concentration time graph, and this is the rate concentration graph. For 0th order, 1st order, and 2nd order, these 3 graphs, they all look different. Okay, and you have to recognize which graph is for which case, okay, below. Starting with rate equals Ka to the power of 0. Okay, so Ka to the power of 0. This is 0th order reaction. 0th order means the concentration term is raised to a power of 0. And like I discussed with you last time, when you raise any number to a power of 0, what does this number become? 1. It becomes 1, okay? And when you raise it to a power of 1, that means A and rate, they are directly proportional. So you see, I'm just changing the order. And just by changing the order, I am changing the effect of concentration on rate. So let me put it this way. So you can make this one first. So you can make this one. Any number raised to a power of 0 means 1. That means when you have 0th order reaction, no matter what the concentration value is, will the rate change? No, because the rate isn't dependent on A anymore if this is raised to the power of 0. No, that means it will be a flat line, it will be a straight line. So can you draw a straight line here? So rate is unaffected by A. Okay, so rate is unaffected by A. That's what 0th order means. So A is the concentration of the reactant. Yeah. What about the second case? So you learn this in math. When you have A raised to the power of 1, that means when I change A, when I drag on the x value here, how will the y value change? It will increase proportionally, right? Because k, you know, is rate constant, it's a fixed number. Let's make it a number, really, that we can work with, 10. Let's just make k 10 now. If A is 1, what will rate be if k is 10? It will be 10. If A becomes 2, rate would then be 20. So you see a proportional increase. When you change A from 1 to 2, you see rate changing from 10 to 20. That means it's proportional, right? It's proportional. That's what first order means. So can you turn this into a statement? So rate increases proportionally with concentration of A. That's what first order means. Okay? And finally, what does rate equals Ka squared mean? Again, let's put a real number into K. Let's make it 10 now. If I put A to be 1, what will rate become if K is 10?
100.
If A is 1, 1 squared will be still 1.
Yeah.
Yeah, so 1 times 10 is 10. What happens if I put A to be 2? Let's say I put 2 in here. 2 squared is
4.
4. 4 times 10 is 40. So that means when I raise the number of A from 1 to 2, you see A went from 10 to 40. That means did it increase proportionally or exponentially? Exponentially, yeah. So therefore, first order, 0th order, and second order, they're just a way to put what I just said. Okay. So we have when we increase the concentration of A, rate increases exponentially. So you certainly know what exponentially means. It's not proportional, certainly. Okay. So with the concentration of A, so that's second order. But no matter which order you're looking at, the concentration must fall over time. Because what does it mean to be a reactant? A reactant used up or a reactant produced in a reaction?
Use up.
They use up. So that means for all three graphs of the concentration time graph, they will fall. But depending on the order, it will fall slightly differently. So I want you to draw it. For 0th order, the concentration time graph will fall linearly. It will fall straight to 0, okay? Yeah. And for first order, it will look like this. And for second order, it will be steeper at first, but less steep at the end. Yeah, so but don't worry, you won't be asked to sketch the second order or the first order. You won't be asked to tell apart these two, other than from one thing, from half-life. So some of you who do physics will have heard of half-life. You have half-life also in chemistry, unfortunately. So can you just select this graph? Yeah. Well, maybe it's fortunate for you, okay, because if you do physics, if you have done this in physics, that means you don't have to remember one more thing. But for those who don't do physics, you have to memorize this new thing, known as half-life. What's so special about the concentration time graph of first order reaction? So for first order reaction, the half-life is constant. Okay, so the half-life, let me put that in purple. So half-life is constant. So half-life, you can write this as T half, T1 half. Okay, and it really means what you think it means. Okay, it is the time it takes. So copy this definition. So it's the time it takes for the concentration, to become half. So self-explanatory, okay, I like this term, half-life, already tell you what it means from the name. So the time it takes for the concentration to drop to half the original value. Let's expand this graph and study it very, very carefully, okay? So half the original concentration. So in physics, this is the time it takes for the radionuclide, okay, to drop to half the original amount. It's the same thing, okay, just that we swap that with concentration. And in here, let's draw a slightly bigger version of this graph. Can you? Yeah, so can you draw this graph? It's expanded, so you have concentration, and this is time. Yeah, and when you draw this graph in here, you will need to take a ruler. Okay, so let's make this original concentration. I don't know what value it is. Let's make it 1. Let's make it 1 mole per dm³. What is half of 1?
0.5.
Yeah, 0.5, easy, right? So we have 0.5 in here. Interestingly, when you look at the time it takes for the concentration 1 mole per dm³ to drop to half mole per dm³, how much time does it take for 1 to drop to 0.5? This much time, right? Yeah, it took this much time for the concentration to fall from 1 to 0.5. And then, what is half of 0.5? 0.25. Yeah, if you are to draw another line here, finding what the concentration is at this point, okay, 0.25, and how much time it takes for 0.5 to drop to 0.25, this would take another half-life. I can repeat this like the whole day, okay, for the whole day, and you will see that the half-life is still constant. Okay, yeah, of course you can say this depends on how I draw the curve, okay, but for the actual curve given in the exam, one way to tell if the reaction is first order or not is by inspecting this graph, the concentration time graph. If a concentration time graph has a constant half-life, it must be first order. So put this very, very important point down in a color that you will not forget, okay, maybe in red. So the half-life, okay, the T1 half of first order reaction is a constant. Okay, so it's a constant. It follows that for zeroth order and second order, the half-life will not be constant. The half-lives are not constant in these two graphs. You can try. Okay, this one very easy to find out. Yeah, so let me also draw you a zeroth order one. Then you will know that it is not constant. So this is the concentration time graph for zeroth order reaction. If I make this 1, this will be like 0.5. This will be 0.25. You can see that the half-life decreases over time. Can you see that? Can you see that the time it takes for it to half, it did not stay constant. It actually decreased. Yeah, so therefore, this you don't need to know. Okay? You just have to know that for first order, it is constant. For anything not first order, it is not constant. That's it. Okay? So I will summarize this for you here. So if the order of reaction is primary or first degree, okay, compared to when it's 0 or second degree, then, so we have an if-then relationship to remember here. So if and then. So then the half-life will be constant for first order. It will not be constant for 0 and second. Is that clear? Okay, so if you like, you can also draw the 0th order thing here. The textbook did not explain to you why that is, but there is some very complex integration, okay, which I will not go to, okay, because not all of you like to do integration. But this one here, this is 0th order. So you can see that the T half, it is not fixed. It becomes shorter and shorter over time. So T half is certainly not constant, right? But on top, what do you see? This is T half. If you take our ruler, I know I'm not drawing it precisely, but the point I want to make here is the T half here will be constant. Yeah, can you see that? So if you like, you can draw this in here. This is how the T half will look for first order, and this is how the T half will look if it is not first order. Is that clear? Okay? Yeah. So that's half-life. Okay. Right, next up we have, okay, and this is a very good example. Can you check out this page? Yeah, the page that says rate equation worksheet.
with respect to ozone. So you can see in this reaction, an experiment was done to decompose ozone at high temperature. That's the only reaction you have. So, and after you read this sentence, you should be able to write an equation. Rate equals K. What's the formula of ozone? What's the formula of ozone? It's O.
O cube.
It's,
No, O to the power of
it's
3.
actually O3.
O3.
It's O3.
Why
Okay.
am I thinking?
Yeah. So yeah, and yeah, so it's actually like from the textbook, but I want you to pick it out and discuss it with you. So, but what is the order with respect to ozone? Explain your answer. Okay, so how do we explain the answer? Can you see that if you are to find the what is that? The concentration of ozone. Yeah. So what do you have in here in this table? Do you see concentration and rate? Yeah. So that means you can plot a concentration rate graph or rate concentration graph, right? Because you only have got rate, can you circle rate and circle concentration from here? Yeah, you cannot plot a concentration time graph using this data because you only have rate and concentration, right? That means you will need to plot the rate against concentration to see whether it will be a straight line that does not rise or fall, whether it will be a straight line that passes through origin, or whether it will be a curve that passes through origin. So what we need to do now is to, we don't have to draw this precisely. Yeah, so you can put the order in here. We don't know what this order is, so let's make it M. Let's make it M right now, okay? And can you take out a highlighter? You have on your worksheet, you have experiment, like a 1, 2, 3, 4, blah, blah, blah. And then you have the initial concentration of ozone, and then you have the initial rate. You know what these two columns they are describing really? They are describing the concentration of ozone, and they are describing the rate. Okay, so what you need to do now is to see how changing concentration affects rate. Okay, so let's do this. We have 1.25. Yeah, we don't really have to use all the data. I want you to just focus on experiment 1 and experiment 3. Can anyone tell me what is the multiple that link these two? Yeah, it's 2. Okay, yeah, it's 2. Can you see how rate changes when I double the concentration? When this is doubled, what happens to the rate? Just look at experiment 1 and 3. It went from 0.8 to, yeah, it doubled. That means, is this a proportional increase? Is it an exponential increase or no increase at all? Proportional. Yeah, proportional increase means, so can you draw this? Draw a pie graph now. This is the rate, and this is the concentration of ozone. Okay? What this table is showing you is that when you raise the value from 1.25 to 2.5, okay, the rate increased from 0.8 to 1.6. So what does this graph look like? It will be a straight line that passes through origin, right? Yeah, okay. And let me show you what the graph would look like if it were of other order. So can you put down the conclusion here? The order with respect to, you see I asked you to explain your answer. So therefore this is how you explain it. The order with respect to ozone is 1. Yeah, why is it 1? That's because when we increase the concentration, yeah, so when we double the concentration of ozone, the rate also doubles, right? So rate also doubles. Let me show you another set of data. Yeah, not this set, okay, a new set. You can copy it down below. There's still plenty of space. You don't need much space for answering the second question. So you can use half of the bottom page there. Yeah, let me show you another set of data. What kind of data will support a zero order reaction? Is when you see this. If I double the concentration of ozone and then the rate does not change, yeah, what will the graph look like this time? Okay, so it will look like this. Let me just copy this. I'm lazy. Okay, so I'll just copy this file here, and I will draw this and that. Do you see what is happening? If when I double the concentration, the rate doesn't change at all. Okay, it is as if the rate just doesn't care, okay, what concentration ozone is. Okay, if the graph look like this, what order would this be? Zero. Okay. Let me show you a third graph that will support a second order reaction, or maybe you can tell me. Okay, if you have a second order reaction, by how much would the rate change when I double the concentration? Yeah, so you can answer this question quietly first, okay? Because I want everyone to think about this. Don't just wait for the answer. I want you to think. If I double the concentration, what would the rate become if this is in this second order? Let's do some math. Okay, maybe I'm not sure if you have math class already today, but let's do this. Okay, to really figure out what this number is, let's make it the unknown. So we want to know what this rate is, right? So if this is first order, sorry, if this is second, if this is zero order, can you tell me when you put 0.8 into here, when you put 2.5 into here, what would the rate become?
0.8.
Yeah, well, okay, when you put 1.25 into here,
One.
and yeah, okay, actually when you put 2.5 into here, 2.5 to the power of 0 will be 1, right? Yeah, so what would the rate become? Well, first we need to find what K is. Okay, when you put the concentration 1.25 into here, and you raise it to a power of 0, 1.25 to the power of 0 will become 1, right? Yeah, so what must K be in order for the rate to be 0.8? It must be 0.8, right? So K must be 0.8. Now that you know K is 0.8, can you try to plug another number in? What is 0.8 times 2.5 to the power of 0? It should still be 2.5 to the power of 0 is 1. But 1 times 0.8 will still be 0.8, right?
Yeah.
Yeah, okay, so what about now? What if you have rate equals K to the power of 2 then? First, when you put 1.25 into here, and you get rate equals 0.8, what is the rate constant? Yeah, so what is K? If rate is 0.8, let me plug this number in. And ozone concentration is 1.25, and this is squared. So what would K be? 0.512. Is it exact?
Yes.
It's exact. Okay, so K is 0.512. Now, in order to solve for this unknown, we plug this in. So rate is equal to K, ozone squared, so you put the K back in. So you have 0.512 times 2.5 squared. So what is the value? 3.2. Okay, so let me write this include that. So 3.2. That means the rate has quadrupled. From 0.8 to 3.2, you know it's quadruple. Okay, so now can you draw this? Okay, unfortunately, this graph is not short enough to show 3.2, but you get the idea. So you have 1.8, 1.6, 2.4, 3.2. That means when I double the concentration, from 1.25 to 2.5, did the rate just double? No, the rate quadrupled, okay? So that means this is an exponential increase, and therefore making this a second order reaction. So can you see what kind of data will support I'll write down the conclusion now. This is first order. A reaction is first order if rate and concentration increase proportionally. A reaction is zeroth order if the rate doesn't change no matter what your concentration is. A reaction is second order if rate increases exponentially with changes in concentration. So, do you see the difference between these three? Yes? Kind of, not quite. No, okay, so this is why we try this question together. So, calculate the rate constant and state its unit. So we already come to this conclusion that it is first order, right? Yeah, so can you put down for part 1? Yeah, question 1, what is the order? We already know that it is first order. Because when the concentration doubles, rate also doubles. So this is why the first order. Can you now rewrite this rate equation properly? Now that you know the order, you don't have to write m anymore. You can write 1. Yes, okay, so therefore we'll turn it into 1. Because the order is 1.
can you now change K as a subject? Because it's asking you to calculate the rate constant. To calculate the rate constant, we rearrange K as the subject. So what is K? K will be rate divided by concentration of ozone. We are just moving things around. So what is the answer? You can plug any of these values in here. You can do 0.8 over 1.25, or you can do 1.6 over 2.5. Let me show you. Using either of these answers will give you the correct answer. So can you try plugging data from experiment 1? And can you try plugging number from experiment 3? Okay, you can try any other experiment. It's okay. So let's try experiment 1 first. What is the rate for experiment 1? 0.8. Okay, so can you do 0.8 over 1.25? Yeah, and that will give a number. Let's calculate later. What about when you, let's say you have a change of mind, you want to use experiment 3. What is 1.6 divided by 2.5? Is it different or the same, the value? It's the same. Okay, they will give you the same rate constant, which is 0.625. 601. 0.64, sorry. Okay, so 0.64, okay. But that's just the number part. What about the unit? Okay, so that's the number part. So to find the unit, do you remember the unit of rate first? Is molar per second or mole per dm cube per second, right? Yeah, so can you put a star around this box? You must remember this. Yes, okay. So can you put down molar per second or mole per dm cube? If you like to challenge yourself, you can write mole per dm cube per second. But yeah, molar per second would do. What about concentration unit?
Mole per dm cube.
Mole per dm cube or just molar? Okay, so mole per dm cube. Can you tell me what would be the resultant unit if you divide the unit of rate by the unit of quantity? Per second. Can you see that this part is gone? Yeah, so the units right now, unit of K will be per second. Okay? Yeah, this is the harder chapter because you can't memorize the unit as the unit is different each time, depending on what order, okay, the reactant has. Okay? Yeah, so can you copy this part? The full answer will therefore be 0.64 per second. Okay, so this is how you find the unit. So how to find the unit of K. And this is how to find the value of K. Yeah, so how to find the value of K. So you see it's different, right? Yes, yes.
Why we don't use experiment 1 and 2?
Why do you not use experiment 2, you mean?
1 or 2, or we choose 1 or 2.
Oh, you can use, I'm just using 1 and 3 to show that any trial will still give you the same answer. It doesn't matter. You may as well use experiment 5, you know. You can try. It will give you the same answer. If you do 3.2 over 5, you will still get 0.64. Yes? Yeah. Okay. So now, let's take a look at another harder reaction. Okay, so I think all of you have done, maybe have at least have tried questions on this. The sulfur clot reaction. Have you all seen or know, do you all know what the sulfur clot reaction is?
No.
It's an experiment where you put a beaker on a hand-drawn cross. And over time, you will be, okay, let me describe this experiment to you. So how we find order of reaction and the sulfur clot reaction. So we have the sulfur clot, and then the harder to understand iodine clot on the right hand side. Okay, so I know now you have a big question mark in your head. What is clot reaction? What does it mean? A clot, oh, if you need to use the bathroom, you can, because it's actually a word. But, okay, so what is a clot reaction?
Can we go?
Yeah. You can, yeah, maybe I'll pause a little bit first. Okay, and if you have a question about the rate of reaction, you can ask me now first. I'll continue when everyone is back. Okay.
just
No
really
idea.
tired.
I think they're just.
Or maybe it's both. Mix of both.
Both.
Yeah,
Maybe it's
probably
raining.
both.
With many reasons.
So how do you feel about the sports day?
How was your sports day?
It's even more busy than work day. I had a very good night of sleep because I'm extremely tired. Wow, very good.
What did you do during sports day?
Sir, you
What
were
did I do?
on the
Yeah.
No. But I was in charge of putting people at the right lane.
Oh.
And once a person becomes seated, he will then like walk around and then I will do the whole thing again. So I have to do the same thing 5 times at least for one single piece. Okay, so yeah, I can tell you it's even more busy than when I would rather I have a normal school day.
What house are you in? Does it
What?
What house?
What house?
Yeah.
Kansai, I think.
Kunzai.
Yeah. So,
Are you running in the teacher relay, student teacher
No.
relay?
I think you would have known if I would.
Yeah, probably.
Yeah, so
No.
no.
Why
I don't want
not?
to embarrass myself. So no.
Sir, can I ask about like in BSc you can get level 5 or what do you need to know?
What do you need to know to get
What do you need to
one?
know? Well, you need to be very like
How many
careful.
percent do you get level
It's
5?
different. It's different each year, but
To be like
To be safe.
safe.
Yeah.
to be safe,
How much percent in the exam?
I really wouldn't call a number because it's really different each year. But I'll just say you need to really pay attention to those traps. If you find 2 very similar answers in the question, yeah, that's really what will tell upon a 5-star like student from just a 5 or just a 5-star student. Yeah, because if you find 2 answers that are very similar, that means you are not like paying enough attention. Because if you cannot narrow down the answer to just one, that means you have missed some details. Okay. Like for example, I remember this question: which of this is the best method for making barium sulfate? Yeah, so there is barium chloride plus.
Hi, sir.
Yes.
Hello.
Yes. What is it?
What happened?
Can I help you?
No, sir, I'm just learning.
Okay. Yeah, so you have barium sulfate. And then the other method is barium carbonate plus H2SO4 bicarbonate. Like barium sulfate. So which
Sometimes
one?
I have problem with remember the like soluble.
Yeah.
Yeah, that's
You need to
the
know the
soluble.
solubility rule. So therefore, in order to really get 5 or you need to at least memorize all the things you're supposed to know, all the facts.
What are we supposed to know?
What are you supposed to know? Well, I have some examples here. So I think
That's info. Very colorful.
just a second. I think I made oh. Yeah, I think I made a worksheet for the Form 5 and I can share with all of you now. Like it's a list of the solubility. Yeah, because they were doing an SPA on the qualitative analysis.
They have
Therefore-
SPA?
Yes.
No,
Not
we
you,
didn't
not
have.
you guys though, because
Yeah,
you
but
have
ours
the
not
COVID.
cancelled.
Well, that may be a good thing. Yeah, because you have. Yeah, thank you. Oh.
I got so high mark in SPA.
So you need to
Did
remember.
Did you?
You need to remember all these. You need to remember all these.
All
Like
these.
which precipitate will we dissolve in excess NaOH or excess ammonia,
Yeah, this one.
and also their color. Yeah, if you really must guess, most of the precipitate here are white. Most. Okay, but some are blue, like copper 2-hydroxide is blue, and iron 3-hydroxide is brown, iron 2-hydroxide is green. Okay, yeah, but most of the other hydroxides they are, like what is that? All white. Okay, and then you will have to know, these solubility rules. Okay, yeah. So therefore, back to that question. Which of these method is best for preparing barium sulfate?
First one. First one?
Yeah, why not the second one?
It's because like that one is like also like a solid.
This is a solid, yes. Okay, so this is why I intentionally left out the stay simple. This is a solid. If you want to form barium sulfate, you should not start with a solid, because if you start with BaCO3, then as soon as you drop it into sulfuric acid, where would the barium sulfate form? It will form on the outside, right, of barium carbonate. So it will prevent further reaction from happening. So this is, I think, a very good example for showing you whether you know what the question is asking. Because if you don't see where the trap is, then most likely you will answer the wrong one. So can you draw the barium? You know this is a shell of barium sulfate, right?
Interesting.
Yeah, which is insoluble. If this is insoluble, it will block the sulfuric acid from further reacting with carbonate, right?
Yeah.
Yeah, from getting in further. You see, it forms a protective shell on the outside.
Uh-huh.
So this is why the second method should not be used, because it will form an insoluble layer of barium sulfate, preventing further reaction. But the first one has no such problem. Why is that? That's because barium chloride is soluble, right? Yeah, so you have barium chloride. So this is BaCl2. That means you have Ba2 plus Cl minus already. So when you pour it into sulfuric acid, yeah, so it will just form like a lot of barium sulfate at the bottom. Okay, so you will have BaSO4. So there's nothing that blocks the reactant from reacting further.
I see.
Yeah, so this is why A is the answer.
Okay.
Okay, yeah, okay, really tricky question here. Okay, so back to where we start. Sulfur clot reaction. So what is a clot reaction? A clot reaction is a reaction that will produce an observable event after some time. You actually have done one clot reaction. You may not know it, but you have done it. When you mix metal with acid, what will you see? Metal and acid.
Gas bubble?
Yeah, gas bubble, colorless gas bubble, right? And you know after some time, gas bubble will not form anymore. That's because the reaction will stop. Okay? And clot reaction, they are reactions that will produce an observable change after some time. So an observable change after some time. So this could be like so after some time, what could the observable change be? So it could be the time it takes for bubbles to no longer form. So for example, you can write Mg plus 2HCl forms MgCl2 and H2. So at first, you will see bubbles, okay, in the reaction mixture. But after some time, there will not be any bubble left. So it will take some time before this event happens. Okay, so this event being the bubbles no longer form. Okay, so in this case, can you write down what the observable event is and what the observable change is? So the observable change is this disappearance of gas bubbles. Okay, so disappearance of gas bubbles. And we will now learn another two clot reaction. Okay, in this chapter they are very hard. Okay, so the first one is sulfur clot reaction. So in sulfur clot, you will have this equation that you need to remember: sodium thiosulfate. Yeah, it's not sulfate, but thiosulfate. So therefore the formula looks a bit unfamiliar. Yeah, it will react with hydrochloric acid to form sodium chloride, sulfur, and sulfur dioxide. So look at the sulfur. What is the appearance of sulfur?
A yellow.
Yeah, it's a yellow solid. Okay, so you must add that it is a yellow solid. And because this is a product, its concentration should rise over time, right? Yeah, it's a product. So when you do this experiment, you will need to mix the reactants in a beaker. Okay, so you mix these reactants in the same beaker. So you have sodium thiosulfate, and then you have HCl in another beaker. So you pour the content from one beaker to another, so that you now have just one single beaker. And then you just have to watch. So your eyes will be set on top of the beaker. Under the beaker, you will put a white tile. On the white tile, you will draw a hand-drawn cross. I mean, you can draw anything. You can draw your name on it. Okay, but a cross will be easier to see. Yeah, so we will tend to draw a cross only in this experiment. So what will happen? At first, there's little sulfur. But after some time, you see when more and more sulfur forms,
it will create like a colloidal solution. Yeah, some very like a milky, okay, solution. Yeah, so eventually there will be so much sulfur formed that you can no longer see the cross. Okay, so this is what you will see at the very beginning. So at first, this is what you see. Well, you see a cross perfectly if you have proper eyesight. Okay, and then after some time.
Whoa.
That's so
So
rude.
true.
No, yeah, trust me, you can see because it's like water. At the beginning, it's clear. Everybody can see it. Trust me. Yeah, but after some time, you will see that it gets kind of hazy. Okay, so maybe this is too
Much.
too much. Okay, so let me use a paler color. Okay, so you see it's getting kind of hazy. Yeah, eventually, if you wait for long enough, you will not be able to see the cross at all. Okay, you will not be able to see. Yeah, and this doesn't cut it. Okay, yeah, so maybe I'll make a darker shade of yellow. So you see, eventually, you will not be able to see the clock. Okay, so from the time you start the reaction to the point you will no longer see the cross, you will need to start and stop the timer. So here you start the timer when you start the experiment. Okay, the moment you mix the two reactants, and you stop the timer the moment you can no longer see the cross, you can no longer make out the cross. So this is the time taken. So can anyone tell me what does the time taken say about the rate? If it takes 4 hours from the moment you start mixing the reactant to you finally seeing the cross disappear, does it mean the reaction is fast or slow?
Slow.
If it takes 4 hours,
So,
slow. Compared to if it just takes 20 seconds from here to there, that
Very
reaction will be faster, right? Do you agree?
yeah.
Yeah. So for this type of clock reaction, can you write down for all clock reactions? Okay, rate is taken as 1 over time taken. So 1 over time taken. Why do we have to reciprocate the time taken? That's because the longer the time taken, this is why we put it in the denominator, because you know the longer time it takes, the slower the rate, right? So this is why we have to do 1 over. Instead of just saying rate equals time taken, why do we do 1 over? Because we want to highlight the inversely proportional relationship here. So this is a very, very important thing to note. So can you put that for all clock reactions, including but not limited to sulfur clock, the time it takes for the cross to block out. Yeah, so can you write down what the observable event is this time? The observable change is the cross will be blocked out. Okay, so the cross will be blocked out, meaning it is blocked by the sulfur. Okay, so why is that? Because the sulfur, so because the sulfur concentration will rise over time. So sulfur concentration will rise over time. Eventually, when the concentration gets high enough, remember sulfur is S8. Okay, so S8. When sulfur concentration becomes high enough, it will mask the cross. Okay, so it will mask the cross. So it's like when you look across the Victoria Harbour when the air pollution problem is very, very serious. You can't even see like the opposite side of the harbour. Okay, so that's the same thing. Wait, except that you're not looking across the harbour, you're looking through this hazy solution into the cross. Okay, eventually it will be blown out. Okay, so that's the sulfur clock. For iodine clock, okay, so some magician will use the iodine clock as a magic trick.
Is it the one where you add and then it turns blue and
It suddenly, no, it doesn't go back and forth. It is a magic trick, you can look it up later, like iodine clock. Initially, the magician will show you like a two clear solution, which he or she will
seen
need you to think it as water. When you mix these
seen
two
this.
clear solutions together, the magician will shake the content.
And
At
then
first it's
come
still not
through.
clear, but after 30 seconds, suddenly it turns all black. It turns black. It's quite scary if you haven't seen it before because you may think that nothing has happened, it's just water.
That's so funny.
When in fact it's not water. The clear solution will suddenly turn blue black. Okay? Yeah, so let's see if I can find you like a
It's on manifestation. Trigger reaction reaction good symmetry.
you can find the video very easily.
1 second
So it's like this.
That is chemistry.
So
Yeah, not magic, chemistry.
I don't know why I'm trying to use the technique so long.
So wow, wow. What kind of math?
Just a moment, just a moment.
Oh.
Okay. Oh, so you see, these two solutions at first they don't. Oh, you see,
That's
that's
it.
it. It's done.
That's what you
Yes, it
said.
is. Yeah, but then yeah, okay. So it's showing you how to do that. The two solutions they are really not water. They are like iodine, okay, and hydrogen peroxide, okay. But when you mix them, yeah, you see after pouring it around for some time, it will suddenly turn blue black. So he's just mixing the reactant.
Yo.
Yeah, so
Yellow.
suddenly, yeah, so this is iodine form. Yeah, so therefore you can see why some people would want to use this as a magic trick.
Okay.
An experiment.
What the solution is that?
It's okay. Let me show you the reactant here because they will ask you questions on this. Okay, so
Really?
Yes, they will ask you questions on this. So we have iodine chlor reaction. So to understand why the color suddenly changed, you need to know three equations. Okay. So the first one is hydrogen peroxide will react with I minus. Okay. To form H2O and I2. So the first task that I need you all to do is to balance this equation. Okay, so balance this equation. Can you identify what is oxidized, what is reduced first?
Iodine is being oxidized.
Oh, iodine
Iodine.
is being oxidized. Okay, don't say iodine is being oxidized. Okay, this is a lethal mistake in DSE. Okay, so write down reaction, the main event here. So the main reaction produces, so it is responsible for producing iodine. Okay, it's responsible for producing iodine. So to balance this equation, can you write out two separate equations? So we are doing a revision of results now. Can you balance these two half equations separately? Okay, so I want you to turn I minus into I2. Help me balance the oxidation half equation. Then help me balance the reduction half equation. So we will check the answer in 30 seconds. Okay, so how do you write the half equation again? You need to balance each of these half equations separately. Okay, I minus has to become I2. Remember we balance the H non-O atom first, right? So in this case it means I. Okay, so we need to put a 2 here. And then we balance oxygen by water, but there's no oxygen on the two sides, so we can skip that. And are there any hydrogen on two sides? No, so we can skip that. Finally, we add how many electrons? 2, yes. But for this one, a little bit more tricky. Are there any non-H, non-O atom?
No.
No, so therefore we balance oxygen next. Which side is missing oxygen? Right, so you need to add how many water here?
1.
1. Yeah, of course. You can also say when you add 1 water here, you put a 2 in here. Yeah, it's okay. Either way, it's okay. So how many H plus do you need to add on the opposite side? 2. And finally, how many electrons do you add on which side?
2 on the right side.
Oh, you add 2
No.
on the
Left.
left. Okay? Because, yeah, remember when you figure out where to add the electron, you do this. You check the charge. So you have 2 times plus 1. So you have 1 times 0. So because you don't see anything in here. And then you have 1 times 0. And then you have 1 times, this is also 1 times 0. Can you see that the sum of charges on the left is 2, right? This is plus 2, right? Yeah, 2 times 1 plus 1 times 0 is 2, right? And on the right, this is 0. So which side is more positive? The left side. So you always add electron to the more positive side. Okay? Alternatively, how do we know electron must report on the left? What do we call this reaction? Reduction, right? Reduction means, is it the gain or the loss of the electron?
Loss.
Reduction is
Gain.
gain. You remember oil rate? what does OR mean? Oxidation is loss of electron. Reduction is gain. When you say something is gain, you make it a reactant. That's what gain means, okay? Because they are needed. They need to gain. They need to be gained by the reaction for it to happen. So reduction is gain of electron. So that's how you know electron is a reactant. When you say electrons are lost in oxidation, it means electron is a product. That's why electrons appear here as a product for this oxidation reaction. And electron appear as a reactant for this reduction reaction. That's another way. Okay, yeah, just be careful. So, what is the overall equation then? So when you add up these two equations, the overall will be H2O2 plus 2I minus becomes 2H2O and just I2. Yeah, just
What about 2x plus?
and then you have 2H plus on the left. Yeah, so you have 2H plus on the left, sorry. So 2H plus in here. So that would be the overall equation. But that's far from done, the iodine clock. This is just the main event, okay? You just need hydrogen peroxide and iodine. The second reaction now. So you have second reaction. Okay, second and third reactions. They are iodine plus thiosulfate will form S4O62 minus and I minus. So this is also a redox reaction in itself. Okay, so what is oxidized, what is reduced? Be careful this time. Iodine is reduced because its oxidation number went from 0 to -1. Yes, so this is reduction. And something else is oxidized. Okay. And then, can you write down the reaction here? This is fast. This is a fast reaction. Because iodine, if there are some excess iodine left, it will react with starch. So for those of you who do biology, you know this. What does iodine and starch react to get? Just tell me the color. Blue, black, which is what you saw, right, in that video. So it will form iodine starch complex. Yeah, iodine starch complex, which is blue-black. So you have this particular shade. Okay, so iodine starch complex is blue-black. And this reaction is slow. And now to fully understand what these reactions mean, you have 3 reactions in total. The first reaction on top is the one that produces iodine, this one, the main event. The second and the third reaction are to consume the iodine. Okay, so you see main reaction produces iodine. Second and third reaction consumes iodine. Okay, but then you have one fast, one slow reaction in here. So let me explain that. So these 2 reactions, they consume iodine. Okay, now let me use an analogy. Think of the first reaction here as you know what you see in the airport. Okay, so you see in the airport the iodine keeps coming out. Iodine are the people who are maybe leaving for the flight, for their flight or something. So you see iodine, they keep entering the departure hall. Okay, so you see iodine, they are being produced by the main reaction. So think of the main reaction as like what happens at the departure hall at the airport. Okay, many iodines are coming out now, and then the passengers or these people here, they have 2 options. They can either go to the fast checkout gate or the slower manual checkout gate. Okay, if you are like a normal human being, okay, yeah, which of those will you go to first? Will you go to the is it called the what was it? No. I mean, there is a gauge where you can just put your fingerprint in there and you can just quickly go through the gate. So okay, I don't know what that's called anyway. So there are 2 counter here. There's an automatic checkout counter, and then there's a manual checkout counter. Yeah, trust me. When I use this analogy, you will know this reaction much better. So the automatic checkout counter is faster. And and the manual checkout counter is lower because there's a guy looking at you asking you what you do, why are you leaving, something like that. So this is lower. No reasonable human being will want to be stuck in here. Okay? Yeah, you want to go there. And so the iodine, when they are formed, they will want to quickly go to the automatic checkout counter first, right? So when would they finally go to the manual checkout counter? Is when all these booths are occupied, right? When all the automatic checkout counters are all occupied, you will then finally be forced to use this, right? So this is what happens. Iodine would at first react with S2, so factory chemistry. Iodine would want to react with thiosulfate first to form the colorless I minus and S4O62 minus. So can you put down these are colorless products? This is why for a moment or two, when you watch that video just now, the initial reaction mixture, even after you can mix it, it still appears colorless, right? Yeah, of course before he makes the reactants are colorless, right? But after he makes the reactant, there's still some time during which the mixture is still colorless, right? That's because all the iodine that are formed, they are turned into S4O62 minus and 2I minus. They are both colors, which is why at first, okay, so now I can draw this. Can you draw hydrogen peroxide in one container? I will show you the video again, but later when you watch the video, you need to know what those containers contain. So one contains Ki, which is a source of I minus. Okay, so this is Ki, so it has some I minus in it. The Ki solution will react with hydrogen peroxide to first form some iodine. But why didn't the color change to blue-black instantly? That's because inside this mixture right now, the iodine will react with thiosulfate to form S4O62 minus and 2I minus. They are both colorless. But why would the solution suddenly turn blue-black then? That's because when all the thiosulfate are used up, just like in our analogy, when all the automatic checkout counter they are occupied, if you really must leave now, okay, you have to go to the manual checkout counter, right? You have no choice. So the iodine, they are forced to react with something else, and that's iodine. Sorry, I mean that's starch, sorry. Okay, iodine will react with starch to form iodine starch. And for those of you who do also biology, you know this is blue-black. So when iodine has no choice but to react with starch, it will suddenly turn blue-black. This is why suddenly the reaction mixture will turn into a very scary blue-black color. Okay, and that means the iodine has now reacted with starch to form iodine starch. And below is what is really happening in here. So at first, in this reaction mixture, you can draw a lot of iodine first. So you have thiosulfate, and then you have starch. So the thiosulfate is analogous to our faster automatic checkout counter here, like this one. So this is the faster one. So thiosulfate represents these. And the starch, okay, represents the slower manual checkout counter here. If your iodine, you will first want to react with thiosulfate first, if you have a choice. Okay, okay. But then after some time, the experiment is designed so that there is not a lot of thiosulfate around. Okay, so after some time, you will have, maybe at first if you have 2 thiosulfate, the iodine can still react with thiosulfate. And after the next moment, okay, you will have only 1 thiosulfate left. And the next moment, you will have no more thiosulfate left. You see there's nothing here. So the iodine are forced to react with starch, which they really don't want to because it's a slow reaction. And then suddenly it will turn blue-black. Okay, so this is a time-lapse video, a time-lapse diagram showing you what is happening at a particular time. So let me show you t equals 0 second, t equals 10 second, t equals 20 second, t equals 30 second. Let me explain this again. At first, you have a reaction that keeps producing iodine, similar to at the airport at the departure gate, like passengers keep coming in, going to the departure hall. They now have 2 different pathways to go to.
One is the faster checkout counter. One is the slower checkout counter. The iodine would want to go to the faster checkout counter first because it's faster. Okay. But then now when iodine reacts with thiosulfate, it will consume the thiosulfate by this reaction. By this reaction here. Because this is the reaction, it will use up the thiosulfate. Okay, it's just as if the guy at the counter, he will walk away with the pendant, right? And then he will leave his seat. Okay, well nobody's sitting there anymore. So there is therefore just one thiosulfate left, right? But then after some time, even this thiosulfate will be gone, right? So you have no more thiosulfate left. Then iodine will have no choice but to react with the starch that it doesn't really want to react with. So, but because these products, they are colorless, but this one is blue-black, that means up to this point, the mixture will still be colorless. But by the time the iodine suddenly reacts with starch, it will suddenly turn blue-black. So do you get a better understanding of this reaction now? Yes, okay, so can you put down the reaction up to which point will be colorless? The reaction up to this point, as long as the iodine is still reacting with thiosulfate, it will still be colorless. So this is a colorless reaction mixture. But then why would the reaction mixture suddenly turn blue-black at this point then? That's because the iodine reacted with the starch to form the blue-black iodine starch complex. So let me show you this, the video once again. So when you go back to here, so you see the experimenter is showing you how to prepare the reactant. So yeah, this is iodine, and that is the I think this is H2O2. Okay, yeah, and then initially he is mixing it, and this will be the other solution like Ki. So this will this is most likely potassium iodide. And then when you pour the solution from the previous mix into here, at first it will look like that. Yeah, I lost track of which is good. But anyway, you know these are just the different substance. I think the last beaker will be starch solution. It will be starch solution. So that's why you have so many things in here. So you see all the way up to this point. Do you see momentarily it turns brown, right?
Yes.
Momentarily it turns brown. That's because momentarily a lot of the brown iodine, iodine is brown, right?
Yep.
Yeah, so that's, you see the brown color just very briefly because the iodine were not reacting with starch yet. But then they are suddenly formed. Yeah, so but by the time this iodine actually will starch, it will finally turn blue-black. Yeah, so what is the observable event in this experiment? It is the time it takes for the solution to turn from colorless to blue-black. Okay, and we can use this to measure the rate. Remember, for all clock reaction, what do? We do 1 over time taken. Yeah, so time taken for the blue-black color to appear. Okay, so imagine this. If it takes only 20 seconds for the blue-black color to appear, compared to if it takes 4 hours for the blue-black color to appear, which will be a faster reaction? The one that took less time. Yeah, less time. So this is why we do 1 over time taken, okay, for the blue-black color to appear. So for the previous reaction, can you add back this description here? It's time taken for the cross to blot out. So for all the clock reactions, there's one common theme, is that there will be a noticeable change after some time. And you just have to do 1 over that to find rate. Okay, so this is what we are seeing now on this worksheet. So can you turn over to the back page? It's the same worksheet but the back side. Yeah, so there should be like a 1, 2, 3, 5 by 5 table there, and then a diagram on top. So there's a cross on the test tube. Okay, so this is basically the same experiment with this brand. It's just that he or she is not putting the cross under the beaker, but he's using a test tube instead. And you will be looking through the test tube. So this is the test tube. You have the cross stuck on the back side of the test tube, and then you are looking at this cross through the test tube. So you're seeing how much time it takes for the cross to block. It's the same reaction, just a variation. So can you explain why, part A now, explain why the volume of sulfuric acid used in each experiment is the same and its molarity is much higher than that of thiosulfate? Oh,
this one, I'll have to explain to you how we find the order experimentally. Do you remember that order, is it related or is it not related to the mole ratio?
No.
It's not related. So how do we find it then? So imagine that I have two reactions. Let's say, can you write this on the notebook first? Sorry. Okay, so how to find order of reaction experimentally. Yeah, so experimentally. Imagine that I have two reactants, A and B. So I have A and B reacting to form C, let's just say. And that's not quite C, let's just call it product. So I have two reactants. Normally, what rate equation can you write when you have two reactants? What are the three components of rate equation? You have the rate constant, yes, small k. And then you have the concentration, right, of the reactant. And the concentration of each reactant will be raised to a power called the order. Yeah, so you can write it in there. Okay. Yeah, so the first thing that you do is, let me put down, consider a reaction with two reactants, A and B. Yeah, so A and B. Now, so you can write down step 1, step 2, so it's easy to follow. Step 2 is that we can write the rate equation as, okay, so rate equation as this. And the rate equation has three parts. Let me remind you once again if you forgot. Rate equation has three parts always. They are number 1, the rate constant. Okay, so number 1, the rate constant. Number 2, the concentration. So these are concentration. So we have concentration of reactants. Note that there can be more than one reactant, so I put bracket S in here. And finally, what do you call those power terms? Order. Yes, it is the order that we're interested to find. Okay, we already should know the concentration of the reactant. Okay, and almost forgot. There's also rate. That makes 4 parts then. Okay, so you have 4 parts. You have also the rate. So the rate equation links these 3 variables to rate. Okay, so the rate equation, so a rate equation links rate, concentration, and order to rate. They will all affect rates, in other words. Okay, that's what rate equation means. Then, how do we find M and N? Well, we need to set up the following experiment. So to find the order with respect to A, yeah, that is M. Yeah, we want to find the order with respect to A, meaning we want to find the power of A. What do? We need to first, we need to react a certain concentration of A, so let's say 0.1 molar of A, with a large excess of B, and see how much time it takes for the observable event to occur. So let's call this, let's say there's a certain rate for it to form the products. Okay, so when you react A with a large excess of B to form the product, you measure a particular rate. Then you will need to double the concentration of A from 0.1 molar to 0.2 molar, and then again mix it with a large excess of B, and then get rate 2. So let's call this rate 1. And here, let's say you have rate 2 now. Okay, I think I should just write it this way. So you have rate 1, and then here you have rate 2. And then now, can you write the rate equation out of these things? So what would the rate equation be when you react 0.1 molar of A with a large excess of B? What would this rate equation become? Let's call this equation star. When you plug these numbers into equation star, what would the rate equation become? For the first experiment, it will be rate 1 equals rate constant times 0.1 to the power of m, right? Yeah, because the concentration of A is 0.1 times a large excess. So large excess can be anything. Okay, maybe I'll make it 2.00. You see 2.00 is 20 times larger than 0.1. Yeah, so therefore we will do 2.00 to the power of n here. So this will give rate 1. And then we will repeat the experiment using another concentration of A. Yeah, and then we will get a new rate. So let's say this is rate 2 now.
Oh, it's.
So we have the same rate constant. So what should we plug for A this time? 0.2. But the order will not be changed when you change the conjugate. The order is still m. Yeah, and that's something that we rely on for this to work. So let's make this 2.00. Can you now solve for m?
Yes.
Okay. Yeah. So let me use the number you see from here. So the okay, maybe I'll give you a number like 3.00 times 10 to the power negative 2. And this is 6.00 times 10 to the power negative 2. So what would this be? Okay, so what would m be if you solve for these two equations? Let's call this equation 1. I know this is very math intensive, but you have to simultaneous equation. Can you divide these two equations by one another? You can use 1 divided by 2 or 2 divided by 1. I would do 2 divided by 1 because I don't want to end up getting a fraction. You can do 1 divided by 2 if you like. So but let's use the shortest and easiest part. What happens when you do 2 divided by 1? Can you see that you have k 0.2 to the power of m, 2 to the power of n, divided by k 0.1 to the power of m. Most of these things you can just ignore. Let me explain. Yeah, because they will disappear anyway. You will see. So you have 6, divided by 3 times 10 to the power negative 2. Okay, can you see how these equations are set up first? Yes. Okay. And which of these terms can you just completely ignore? 2 to the power of n, because it's the same term on both sides, right? So take it out. No need to worry about it. K can also be taken out. Times 10 to the power 2 can also be taken out. What can this whole expression be reduced to? It's 0.2 to the power of m over 0.1 to the power of m equals 6 divided by 3, right? Now we need to use log. You need to use log. Do you remember how to use log?
No.
No. Okay. Well. Okay. Here, let me put this down. You need to also know index log, unfortunately. So you have a to the power of m over a to the power of n means a to the power of m minus n, right? Yeah. And similarly in math, when you have a to the power of n times a to the power of n, this is a to the power of n plus n. Now, what about the log rule? Log rule you should also know. Log a to the power of b means b log a. Yeah, you need to at least know these 3 rules. So let's do this. Can you simplify this? What is 0.2 to the power of m divided by 0.1 to the power of n? Oh, then that means there is another rule here that I should also add, which is similar to the second rule in here. Yeah, it is m to the power of a over n to the power of a. It will be m over n all to the power of a. So this is the 4th rule. Okay, so can you use these rules to turn this statement into a simple one? Can you use the last rule?
What's wrong, sir?
Yeah, I know. What's wrong then? Are they doing some exercise?
Like right before
Sir,
the
they
second
might
day.
be
I don't know what they're doing.
What are they doing?
What are they doing?
I don't know.
Standing up, sitting down.
So why would the teacher tolerate that? I don't get it. They do it every lesson.
Cameras and
I really don't get it.
cameras
So, okay. Anyway, back to it. Let's not let them describe it. So 0.2 to the power of m over 0.1 to the power of m. Can you apply this? What would this simplify to? It will simplify to 0.2 over 0.1 all to the power of m. And what is 6 divided by 3?
2.
2, yes, okay. And that means you have 2 to the power of m equals to, what must m be?
1.
1. M is 1. So much work for just one thing, right? But don't worry. Yeah, we have many trials in here. You can use any 2 trials as long as the concentrations are of one reactant are equal. So can you see that in here we are changing the concentration of one reactant while we keep the concentration of another reactant. You can't change both reactants at the same time. Why? Because if you change both reactants concentration at the same time, will you be able to take that term out? If these two numbers are different, 2 and 2, if these two numbers are different, will you be able to take this out? No. If you are not able to take this out, you will have two unknown in one equation, which is unsolvable. So this is why we have to
Keep
keep
one.
one of the concentration to be unchanged while we change the concentration of another reactant. Okay? So to show you how this works, can you really come back to this page? You need to do some conversion now. Tell me how many reactants are there on this page. So you have S2O3 2 minus plus 2H plus give you blah blah blah. So you can just
Blah, blah,
dismiss those as products. The products on the right doesn't concern you. The question is asking you about the reactant. So let's just set our eyes on these two reactants. So let's make this A and let's make this B. Okay? I should just highlight the H plus. The 2 is just the mole ratio. The mole ratio has nothing to do with the order. So don't say that, oh, this is a mole ratio of 1, this is a mole ratio of 2, so the order is 1 and no. That's BS. Okay, that's not how it works. Okay? So we will first write out the rate equation. Can you write me the rate equation?
Yep.
Rate is K S2O3 2 minus to the power of M and H plus to the power of N, right? You can also make it A or B. Yeah. This is not like equilibrium. This is not like equilibrium. Okay? Right. So can you now tell me, okay, so you have experiment 1, 2, 3, 4. This is a pretty hard question. So you have volume of 2mH2SO4, and this is volume of 0.25 mNA2S2O3. So I think the question is just making it more complicated by scrambling the order of the reactant. The 0.25 molar Na2S2O3 really is describing this reactant. The 2 molar H2SO4 really is describing this reactant. So you can maybe flip the equation around to make it easier to see. But then, this is not even the trickiest part. The trickiest part is that you're mixing these two solutions together with water. Can you tell me how much volume of water are there in total in all 3 experiments? You can pick any 2 trial, any one trial. How much total volume do you have if you add up this number with this number with this number?
8.
Yeah, it's always 8. So if you take the first example here, this is no coincidence. 4.5 plus 1 plus 2.5 is 8. 4.5 plus 2.5 plus 1 is also 8. So all these will have the same volume. Yeah, and do you remember learning this equation in Form 5? Okay, in dilution.
Oh, M1V1.
Yes, M1V1 equals C1, M2V2. Does anyone remember what M and V stand for?
Yep.
M is not mass, M is molarity. Molarity. V is
Volume.
volume, yes. So 1 means before dilution. 2 means after dilution. Okay, so 2 means after dilution. And M means molarity or concentration, while V stands for volume. So really this equation, it has one purpose only, is to find the new concentration after dilution. Can you make M2 the subject?
Yep.
Yes. What will you have on the other side?
M1V1.
Yes, I like to group terms together. So you can of course write M1 V1 over V2, but I like to write M1 times V1 over V2 because this is a ratio. Okay, so now we need to find the concentration of like the H2O3 2 minus H2SO4 after mixing. So you see these concentrations, they are before mixing, right? They are the concentration before mixing. 0.25 molar means before the thiosulfate is mixed to the other reactant, what the concentration originally was.
2.
Um,
Oh, wait, no.
Yeah, 0.25 means by itself is 0.25 molar. It hasn't yet mixed with other stuff first. But after you mix it with the H2SO4 and water, the total volume becomes 8, right? So what is the new concentration? So can you turn this into the new concentration of S2O3 2 minus? And the, so maybe I'll turn it into Na2S2O3 first, and H2SO4, the concentration. And for water, you don't have to calculate the concentration because the water is here just to dilute it. Just to dilute it. So can you tell me what is the new concentration of Na2S2O3? This will be M1 times V1 over V2. So what is M1? 0.25. What is V1? V1 will be this number, 4.5. Yeah, what is V2? Yeah, 8. Remember V1 means the volume before dilution. So volume before dilution. And V2 means the volume after dilution. So what is 0.25 times 4.5 divided by 8? 0.125. Okay, so 4.5 divided by 8. So 0.125. What about H2SO4? What is the number here? This is 1, right? So therefore, what would the equation become? M1 times V1 over V2. What is M1 first? 2. So M1 is 2. So 2 times,
You're changing because like the volume of like.
because you are
SO4
changing.
is 4.5. It's not 1.
Oh, you mean this one is, this is,
Oh,
this is-
yeah.
oh, right, yeah, because I swapped it around, yeah, so sorry, yeah, so then this should be 1, I bet. So this should be 1, yeah, so, but yeah, in Excel, don't worry, you will have enough space, and, you will have like swap it, and I don't think they will like just swap between the right. So you have 0.25 times 1 divided by 8, which is which is 2, I think. Which is 2. You can try. This is 2, right?
No.
No.
0.03125.
1. Okay, so 0.03125.
Yep.
Okay, and what about this number here? This is 4.5 times 1 over 8. 5625. Can you see that this number is much larger than that? Yes. So that means
It's not 1. It's 4.5. It's 4.5. The volume
4.5
times
times
0.25.
Okay, 2. Okay, right. So this, yeah, this should be 2 times 4.5 divided by 8.
8.
So it's 1 point something. 1 point. Still, this number is much larger than this. Yes. Okay. So we have this equation now. So we have what is the rate for this experiment? Can you see that the time for complete disappearance of the reference line is 103 seconds? What is the rate? Rates can be found by dividing 1 by this number, right? Yeah, 1 over 103. We don't have to actually simplify it, okay? We can just write this as rate. So for this question now, you have to convert all these into H2SO4 and Na2S2O3 using the same technique. Okay, can you write this number by the side? Yeah, you should have some enough space on the side. Okay, let me show you the steps you need to take. So you have 1, 2, 3, 4. To find the concentration of H2SO4, you need to take the original concentration, 2 times this number, then divide by the total volume, which is 8. So next to this number, let me write out what you should do. You have 4.5 times, you have 2 times 4.5 over 8. This will be the value that you need to put for H2SO4. Okay, what about for Na2S2O3? The number you see here is 1, right? That means the concentration should be, how do we calculate it? 0.25 times 1
Over 8.
divided by 8, yes. After we are done with all this is a really nasty question because it is not really H2SO4 that is the reactant. Can you see what the reactant really is? Other than that, it's H plus, right?
Oh, yeah.
Yeah, so therefore you need to do one more step. Okay, yeah, this is really tricky. No. How much x plus would that be if you have x more predictable?
Times 3 times 2.
Times 2. And you need to times it by 2 as if it's not complicated number question. So, okay, we'll have to, okay, let me do it step by step here. Okay, but this is just a slightly harder question than normal. Yeah,
Oh my god.
can you tell me what this number is? And after you multiply it, what will this become?
It's about 4.5 over 4.
2.254.
No, 2.5.
2.25. After you multiply that by 2, right?
Yeah.
Yeah, okay. And then we have to do another conversion here as well. But this one, you don't have to really do anything. Because each thiosulfate, each sodium thiosulfate has how many thiosulfate?
1.
1. So therefore the number in here is the same number as you get in here.
Yeah.
So what was this again? What would this give?
0.03125.
Okay, so now we need to do this for all the other trial, unfortunately, but I want your involvement. Okay, can you also find the rate? The rate is equal to 1 over time taken. And to save you the trouble of really finding it, you can just express this as a fraction. So we have 1 over 103 for the first trial, and we are just done with first trial. So can you do this for the other one? We'll check the answer in 1 minute. Okay, yeah, in 1 minute. Yeah, but yeah. So I'll pull out the calculator as well.
Why are you so? I'm like lost. Sir, what question we are like answering? Wait. Are
Yeah.
we asking an answer for the part A?
We are actually finding the answer to part C and D already.
Oh my
Okay,
God,
but okay,
what
for
about
part A, why must the volume of sulfuric acid used be the same? Because do you want to change the so the volume is the same. This is because you want to find the order of thiosulfate. Remember in our previous discussion here, why do we have to keep the concentration of one reactant to be much larger? Because we want to eliminate it from the expression, so that we have only one unknown here, right? Yeah, think about what happens if this is not the same, if these two values are not the same. If they are not the same, would they be able to cancel out? If they are not able to cancel out, how many unknowns would you have in the equation?
2.
You have 2. Can you solve an equation with 2 unknowns?
No.
No. So therefore, this is to ensure that, so explain why the volume of H2SO4 used is the same. So this is to ensure that its concentration is constant. Can you write out the answer to the first part? This is to ensure that the concentration of sulfuric acid is a constant. Why is this step so important? So that the order with respect to Na2S2O3 can be found. Okay? Yeah. If you use this numeric example again, it's like asking you why must these two numbers both be 2? Why can't they be different? Because if they are different, you will not be able to cross out this term at the end. If you're not able to cross out this term, there will be 2 unknowns. This equation will not be solvable. So for this question then, you will just say, because we want to make the concentration of sulfuric acid constant, the 2 and 2 means they are constant, so that the order with respect to the other reactant, thiosulfate, can be found. Okay, so that's for part A. And yeah, for what we have been doing so far actually is solving for, so for part B we already know the answer. How is the time recorded related to the initial rate? We need to divide 1 by the time taken. So what about the answer to part B? So for part B, the rate is equal to 1 over time taken. So this is how the time taken is related to rate. Yeah, and here let me also put down the answer to part A. Yeah, so this is to ensure that the concentration of H2SO4 remain a constant. Okay, so the order with respect to Na2S2O3 can be found. If this is also a changing
number, we will not be able to solve for the order of thiosulfate. So now, can you tell me what are the answers to these other boxes? So let me write out what this number is here first. So you have 4.5, you have 4.5. Oh, you don't have good news. You don't have to do this for H2SO4 anymore because we have done it already. So we have this number, this number, this number, this number. So that means all these numbers here will be 2.25. 2.25. Because they are the same numbers. The only thing you need to do is to find the concentration of thiosulfate. So 1.5, 2.0, 2.5. So what's the real concentration of thiosulfate here? Yeah, times 1.5. Yes, so you have 0.25 times 1.5 over 8. 0.25 times 2 over 8. 0.25 times 2.5 over 8. So
What is that?
what is that? Okay, so you have 0.25 times 1.5 over 8. So this is 0.04688.
My head is hurt.
And then 0.0625. And then you have 0.25 times 2.5 divided by 8. So 0.07813. So can you see that? Okay, can you now tell me what the order is? Okay, when you look at this concentration.
Huh.
Yeah, so what is the rate for the second and the third and the fourth experiment again? It's 1 over 68, 1 over 50, and 1 over 40. Now it's up to you. You can pick any two trials. Which two trials do you like? Doesn't matter.
The first two.
Okay,
It's
okay.
simple.
Yeah, half of least resistance, right? Okay, so we'll just use this one here. So let's call this experiment 1, experiment 2, experiment 3, experiment 4. Can you plug these numbers into our rate equation now? So the rate equation, remember before, it is rate equals K H plus to the power of M S2O32 minus to the power of N. If you say you want direction, experiment 1 and 2, let's plug them into this equation. What would the equation become? For the first experiment, it will become 1 over 103 equals K times 2.25 to the power of M, 0.03125 to the power of N, right? For the first experiment.
I don't know.
You don't know. Do you see I'm plugging this number H plus into here?
Oh.
And I'm plugging this number 0.03125 into here.
Oh, yep.
Yeah, and then I'm plugging rates into here. So this is why I put them in each position. So the order is still not known. So now it should be immediately obvious why H plus has to remain constant. Because if H plus is not constant, then you will have two unknown, right?
Yep.
Yeah, okay, so now can you try to put experiment 2, the data from experiment 2 also into the same equation? Tell me what will it become? It will become 1 over 68 equals K times 2 to the power of M 4688 to the power of N. So now, remember what we said? You can manipulate this equation. Do you want to do 1 divided by 2 or 2 divided by 1? Doesn't really matter. 2 divided by 1. Okay, let's do 2 divided by 1 then. So we have, you see there's at least 2 terms you don't have to worry about. It's the K and the 2.25 to the power of N, right? Because they are found in 2 equations. So let's do 2 divided by N then. 2 divided by 1. So you have 2 divided by 1. So which term would be crossed out? The K, yeah, the 2.25 to the power of that is a different color. So this is gone, this is gone. So you have, still a very scary number. Can you first do 1 over 68 divided by 1 over 103? Make sure you type it properly.
103 over 68.
Yes, it means 103 over 68. That is, that will be a weird number. Doesn't matter. You can also do this thing now. What is 0.04688 over that? You can just,
This one?
yeah, let me also find this. So 103 divided by 68 is,
Yeah, only because I take 1 divided by 2, not 2 divided by 1. Actually, it's the same.
so 0.04688 divided by 0.03125. Okay, oh, so the answer is out. So you have 1.5 to the power n. So what must n be then? If 1.51 is equal to 1.5 to the power n, it's close enough to the number,
3 over 2.
but I mean n.
And
N?
N is close enough to 1, right?
Log.
Because
Oh,
these
it's
two
not.
numbers are very similar, right?
Very similar. It can be only 3 orders.
Oh, okay, I think I know why you don't get this. Because this number, now, like you said, you did not report the accurate number, right? You rounded it off, right? Because of rounding, this is why this number is not exactly 1.5. But in reality, it should be 1.5. Yeah, so n must be 1. Because only when you raise 1.5 to a power of 1 will you still get 1.5, right? If this were 2, this will be a very different number, right? If this was 0, this will be 1, right? Okay, alternatively, how do we find n is equal to 1? Yeah, the alternative way involves log. Okay? So can you tell me if you have, okay, if a is equal to b to the power of n, how do you find n? You need to-
Log equal to log of
you need to
A
log-
by log B.
Yes, you need to log both sides. Log a will be equal to n log b. Okay, let's see how I
Real
can
big
put
one.
it this way. Okay, what if I have a number? If I have 2n to the power of 4, I know of course at a glance you know n is 2, but how do you really show me that n is 2? You need to log both sides, right? Let's do this. I mean, you cannot see that n is 2, right? But that's just your instinct, your gut feeling that n is 2. You can't say it's gut feeling on the exam, right? You need to actually show it, right? So, we log both sides. So when you log 2 to the power of n, and you log 4, you can then write this as n log 2 equals log 4. Yeah, it's more complicated than you think, okay? And finally, how do you solve for n? Is to do log 4 over log 2. We are just doing the same thing here. So let's try this. The example we were given just now is 1.51, 1.5 n equals 1.5. So can you use log again to solve this? 1.5 to the power n means 1.51. What is n? Can you solve this? It will be log 1.5 to the power n equals log 1.5, right? Yeah. So can you solve for n? So by the way, how did we go from the second step to the first step? You may ask. That's because when you have log a to the power of b, this will become b times log a. And this is another log rule, okay? And this is the only other way to go yeah. So you have n log 1.5 equals that.
1, 0.
So can you type this on the calculator? N is close enough to the number 1, right?
Yeah.
Yeah, so you can try, it will be either 0.99 something or 1.000 something, okay? Which is close enough to 1, okay? Yeah. Well, this is like a heck of a question, okay? Yeah, really complicated. But how do we find the rate constant? Do you remember, to find the rate constant, do we really need to worry about which experiment to use?
No.
No. Can you pick maybe we'll do this in groups, okay? So maybe like Leo and why you can work on the first experiment. I want to
Those
check if
people's
the
names.
That's
What
the
about me, sir? Sir,
Easy.
who am I? Sir, who am I?
I find your name very difficult to pronounce. I think
It's because your name on the actual thing is different.
No.
No.
Just call it Daisy.
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 Daisy, like the flower, you know?
Okay, right, yeah, so
I'm flourishing.
Okay, sleep. Yeah, you and can you
I'm
work on
failing.
this? Can you help
I'm
me
flourishing,
solve?
mother.
Now that you know the order is like again, what is it? It's
Zero point
basically the order.
zero something. It's close to
But
one,
you need to
so it's equal
also
to
know
zero.
the-
Let's do
Just like you have to use like
Do you know the M
three
one?
significant
Yeah, okay, so the time for calculating the
It's
rate.
the same. It's the same. It's equal level.
Okay. So it didn't say what the order is for sulfuric acid.
No, do we have to find it?
Then, oh, so for this one.
So the order is.
So okay, maybe not this question then. So let's try the other one. I think some information is missing in here. Some information is.
What about B? We don't do B. B.
Yeah, what about the
The
yeah, I
order
think
you
about it,
need
there's
order
something
of
missing.
each person
So
for
not using the same
don't
amount
know
of
what it
acid but different initial concentration
four.
of
What else
sodium
is it?
thiosulfate. After doing this, you can only find the order with respect to thiosulfate. And
Because you know
then
that you just substitute it to and you will find.
yeah, so you can
substitute.
you can then just put back n to be 1. Okay, yeah, you will have this equation rewritten as what? This will be rewritten as rate equals k h plus to the power of m and S2O3 2 minus to the power of 1, right? Yeah. So you need to then find two trials.
Wait, but they're both the same, so they'll cancel each other out.
Yeah, so they will cancel each other out anyway. I think maybe there's something I missed in this question. Okay, don't worry about part B first for this page. Don't worry about part B.
Okay.
I should have.
What about the rate constant?
okay.
What is that?
Hey,
Can you try? Okay, question 4 you can totally do it. Yeah, question 4. Okay, let's
Oh.
skip question 3 for now. So for question 4, can you calculate the order with respect to? This is the type of the question. Question 3 and question 2 they are too hard. I think. Okay, yeah, especially
The
question 3.
weird mental
Yeah, question 4
damage.
is the typical level of DSE question.
Like we need break. Only 3 minutes left.
Oh.
We damage the
okay,
mental
is there a
damage.
question?
So okay, for those of you who think you don't need a break, you can work on this first, okay? And like I will discuss the question with you. Yeah, so you can maybe try this question. Just try one more question, okay? Like this one.
I'll do
The
it.
first step is to write the rate equation. How many
Not that
reactions do you have?
Not that one. Here.
one.
How many reactions are there for this reaction? There are 3. So therefore, you should always start by, what do you include in the rate equation? Rate constant,
No, third page.
and then IO3 minus the first reaction, H plus the second reaction, and I minus the third reaction. So now you can make the order ABC. Yeah, I don't use M and N because I don't want to make that O. If I make that O, it will be like 0, see, so I want to make it ABC, make it clear. Now, can you find 2 trials where 2 of the reactants are constant, but 1 of the reactant is changing? Which 2 trial has 2 of the reactants concentration being equal and just 1 of the reactant concentration changing?
1 and 2.
1 and 2. So you see when you plug 1 and 2 into here, the equation becomes 0.5, 1.0 equals K, 0.001 to the power of A, 0.0001 to the power of B, 0.0001 to the power of C. And so what would the second equation become? It will be everything unchanged except the first one, right? Yes. So can you tell me which unknown can I solve by dividing these 2 equations?
A.
A, yes. Okay, so can you solve for A? You can ignore the other ones, please.
Yay.
Yeah, so, okay, let me just show you the answer. So it's 1.0 divided by 0.5 equals just 0.0002 to the power of A divided by 0001 divided by multiplied to the power of A. So what is A?
What is A?
What is A?
I don't know.
You know this will be 2 to the power of A.
because this expression will now be common. So what must A be? A must be 1, right? Yeah, so and okay, I want you to work on the other ones, but still I want you to tell me what you can work from experiment 3 and 4. If you compare experiment 3 and 4, which order can you find?
C.
C. Yeah, because can you see in 3 and 4, the concentration of the first two reactions are unchanged this time, right?
Yeah.
So the last one is changed. So by comparing 3 and 4, you can find C. And finally, by comparing which two, can you find B?
Yeah. Any of them.
1 to 3.
1 and 3. Yes, 1 and 3. So do you see this is the type of DSG level question? The one on question 2 and 4, they are too hard. Okay, they are too hard. So, but you can try question 4 first and tell me the answer next time. Okay?
Next week.
Yeah, next.
Tomorrow.
Tomorrow. We have one lesson tomorrow.
Just one lesson tomorrow.
No, tomorrow I have typhoon.
Lady.
Okay. Yeah, so if you have questions, you can call and ask me now because I didn't need.
Sir, I have a question.
Okay.
Do you think any of us will pass the DSC?
No, we'll
I